Tonight, we're going to talk about a spacecraft that left the solar system 14 years ago and is still inside it. Both of those statements are true. Neither is a trick, and the gap between them is the strangest thing about the most distant object humans have ever made. Voyager 1 launched in September of 1977. It is still flying, it is still transmitting, and tonight it sits about 15.8 billion miles from where you are. In August of 2012, it crossed a boundary called the heliopause, and the headlines that week said it had left the solar system. That was reported everywhere, and it is the version most people carry. The Sun's gravitational reach extends roughly 600 times further than the point Voyager has reached, so it did not leave. It got out of the bubble of particles the Sun blows around itself, which is a real boundary and a genuine achievement, and it is nowhere near the edge of the Sun's actual territory. On current speed, it needs about 300 years just to reach the inner edge of the next region out, and something like 30,000 years to pass beyond it entirely. Voyager will not survive that. It will not survive the next decade. Its power source has been decaying since the day it launched, at about 4 watts a year. 8 of its 10 instruments have already been switched off, 3 of them this year. Engineers are now fighting for individual watts to keep one instrument running into the 2030s. So here is the shape of tonight's video. The spacecraft dies around the end of this decade. The departure takes 30,000 years, which means the working machine, the thing that talks to us, never leaves the solar system at all. Only the wreckage does. There is also a date coming, and it is close. On November 13th of this year, Voyager 1 will be 1 full light day from Earth. A signal from it will take 24 hours to arrive. Nothing humans have built has ever been that far away, and it happens in under 3 months. By the end of tonight, you will know exactly where it is, how it got there on an alignment that comes around every 176 years, what it found at 4 planets, what actually happened in 2012, why the solar system is far bigger than the coverage implies, how much power is left, what the final transmission will be, and what remains on board afterward. Everything measured will be called a measurement. Everything projected will be called a projection. And where the honest answer is that nobody knows, you will get that instead. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Start with where it actually is, because the number moves while you are listening to it. Voyager 1 is currently around 15.8 billion miles from Earth. In the unit astronomers use for distances inside a solar system, that is about 170 astronomical units, where 1 astronomical unit is the distance from the Earth to the Sun. So Voyager is 170 times further from the Sun than you are. It is moving away at about 38,000 miles per hour. That works out to roughly 325 million miles a year, which means the distance grows by about 3.5 astronomical units every 12 months. If astronomical units are unfamiliar, the reason astronomers use them is convenience. Writing 93 million miles repeatedly is tedious, and most of the distances inside a solar system are small multiples of it. 1 astronomical unit is Earth to Sun. Mars is 1.5, Jupiter is 5.2, Saturn is 9.5, so the whole planetary system, out to Neptune, fits inside 30 of them. Once you are past that, the unit stops being convenient and starts being the only way to talk about the region at all, because light years are far too large and miles produce numbers with too many digits to hold. Now the comparison that makes 170 astronomical units means something. Neptune, the outermost planet, orbits at about 30 astronomical units. Voyager passed that distance in 1989 and has since gone almost 6 times further again. Pluto averages about 39. Voyager is more than 4 times beyond it. The New Horizons spacecraft, which photographed Pluto in 2015 and is the second most distant working probe, is at around 62 astronomical units. Voyager is nearly 3 times further out. Voyager 2, its twin, is at about 140 astronomical units. It travels slightly slower, and it took a different route. You may be wondering why Voyager 1 is further out than Voyager 2 despite launching later. Section 2 answers that properly, and the short version is that they took different routes, and one of them was thrown harder. So the running order of the most distant objects humans have built is Voyager 1, then Voyager 2, then 2 Pioneer probes that stopped transmitting decades ago, then New Horizons. You have a reference point for 38,000 miles per hour, even if it does not feel like one. A commercial airliner cruises at about 570 miles per hour. Voyager is moving roughly 66 times faster than the plane you have sat on. The International Space Station orbits at about 17,500 miles per hour, and that is fast enough to circle this planet every 90 minutes. Voyager is going more than twice that. A rifle bullet leaves the barrel at somewhere around 2,000 miles per hour. Voyager is 19 times faster than a bullet, and it has been doing it without stopping since 1977. And here is the part that undercuts all of it. At that speed, after 49 years, it has covered a distance that light crosses in under a day. That gap between how fast it seems and how little it has covered is the whole difficulty of interstellar distance, and no amount of engineering closes it. Speed is not the problem. The distances are simply not on the same scale as anything a chemical rocket can do. There is one spacecraft that is faster, and the comparison is instructive. The Parker Solar Probe reaches around 430,000 miles per hour at its closest approach to the Sun, which makes it by far the fastest object humans have built. But it is fast because it is falling toward the Sun, and that speed is at the bottom of the dive. It is in orbit. It is not going anywhere. Voyager is slower, and it is leaving, and leaving is the harder thing. Now the light travel time, because it is the number that makes the distance real in a way miles never will. Radio signals travel at the speed of light. At 15.8 billion miles, a message from Earth takes about 23.5 hours to reach Voyager 1. Send a command tonight, and it arrives tomorrow night. If you want confirmation that the command worked, the reply takes another 23.5 hours, so a single question and answer with this spacecraft takes nearly 2 days. That is not a communications inconvenience. It is the reason every action has to be planned weeks in advance and loaded as a sequence, and it is why the people who operate it describe the job as writing letters rather than having conversations. That delay has a consequence you may not have considered, which is that nobody operating Voyager has ever known its current state. Every piece of information about the spacecraft is at least 23.5 hours old when it arrives. If something failed last night, the team will not know until tonight. So the engineers are always working from yesterday, and any command they send is answering a situation that has already moved on by 2 days by the time it takes effect. They have been operating that way, with the gap widening every year since the 1980s. Which brings us to November. On November 13th of 2026, that one-way travel time reaches exactly 24 hours. One light day. Voyager 1 becomes the first object built by human beings to be a full day of light away from Earth. That milestone is worth understanding properly, because a light day sounds small next to a light year, and it is not small at all. A light second is about 186,000 miles, which is most of the way to the moon. A light minute is about 11 million miles. A light hour is about 671 million miles, which is roughly the distance from the Sun to Jupiter. A light day is 24 of those. about 16.1 billion miles. Voyager crosses that line in under 3 months, 49 years after it left the ground. And here is the part that puts the whole video in proportion. 1 light year is 365 of those light days. So after 49 years of continuous flight, at 38,000 miles per hour, never stopping, never slowing, Voyager 1 is about to complete 1/365th of a single light year. The nearest star is 4.24 light years away. Nobody is claiming Voyager was aimed at another star, and I do not want that comparison to sound like a failure. It was built to photograph planets, and it did that. The point of the number is calibration. When you hear that something has left the solar system, this is the actual scale of what leaving means. One more thing about the distance, because there is a way to hold it that works better than the raw figure. If you shrank the solar system so that the Earth's orbit was the size of a dinner plate, roughly a foot across, then on that scale, Neptune would be about 15 feet away, and Voyager 1 would be about 85 feet away, which is most of the length of a swimming pool. The nearest star, on that same scale, would be about 14 miles away. So the whole planetary system is a dinner plate. Voyager is at the far end of a pool, and the next star is a 14-mile drive. That is the geometry the rest of tonight sits inside, and it is the reason the word leaving needs so much care. There is one number in this section that will have changed by the time you hear this, and I want to be honest about which. The distance. Voyager adds about 325 million miles a year, so the figure of 15.8 billion is accurate for roughly the month this was written, and will creep upward afterward. Everything else here is fixed. The speed, the light travel time as a rate, the November date, the comparisons to Neptune and Pluto and New Horizons. If you want the live figure, NASA publishes it and it updates continuously. Watching that number climb is a slightly hypnotic thing to do, and it is the only way I know to make a distance like this feel like it is happening rather than being described. Voyager 1 is 15.8 billion miles out, 170 astronomical units, moving at 38,000 miles per hour, and a signal from it takes just under 24 hours to arrive. In November, it becomes the first human object a full light day away, which is 1/365th of a light year, after 49 years of flight. The mission only existed because of an accident of timing, and if it had been proposed 20 years earlier or 20 years later, it could not have been flown at all. That is the second section, and it is about a geometry that comes around every 176 years. Start with the problem the mission was solving. Reaching the outer planets with the rockets of the 1970s was, on the face of it, not possible in any reasonable time. Getting a useful payload to Neptune on a direct trajectory would have taken decades and more fuel than anything then available could carry. The way around it is called a gravity assist, and it is worth explaining plainly because everything in this section depends on it. A spacecraft flying past a planet is pulled in by that planet's gravity, swings around it, and is flung back out. From the planet's point of view, the spacecraft arrives and departs at the same speed. Nothing is gained. But the planet is also moving in its own orbit around the Sun. And relative to the Sun, which is the frame that matters, the spacecraft comes away with some of the planet's orbital momentum. The spacecraft speeds up. The planet slows down by an unimaginably small amount because it is unimaginably heavier. That technique was worked out in detail in the early 1960s. A graduate student at the Jet Propulsion Laboratory named Michael Minovich did much of the mathematics, using the fastest computer available at the time to run the calculations by hand methods that had previously been considered impractical. Then, in 1965, another JPL researcher named Gary Flandreau was asked to look at ways of reaching the outer planets, and he found something in the orbital data that changed the program. Jupiter, Saturn, Uranus and Neptune were about to line up, not in a straight row, which is the image the word alignment usually produces. They were going to be arranged along a curve such that a single spacecraft, launched in a narrow window in the late 1970s, could swing past all four in sequence, using each one to reach the next. The arrangement recurs roughly every 176 years. The last time it had been available, nobody on Earth had electricity. The next time will be in the 2150s. Flandreau's calculations showed the trip could be done in about 12 years, instead of the 30 a direct flight would need. That is the whole reason the mission happened when it did. Not ambition, not funding, not politics. A window that opens twice every 3.5 centuries happened to fall during the decade when the technology to use it existed. There is a piece of political history attached to that window that is worth knowing, because the mission you have heard of was not the mission that got funded. What Flandreau's calculation made possible was a 4-planet tour, and that is what the scientists wanted. It was proposed under the name the Grand Tour, and it would have involved multiple spacecraft covering the outer planets and Pluto. It was too expensive. The Grand Tour was cancelled in 1972. What survived was a smaller, cheaper program called Mariner Jupiter-Saturn 77, approved for 2 spacecraft to visit 2 planets. 4 years of operation. That was the funded mission. But the people building it knew what the alignment allowed, and they built the spacecraft to a standard that would survive far longer than 4 years, and they aimed Voyager 2 on a trajectory that kept the option of continuing to Uranus open without ever quite saying so in the budget documents. The name was changed to Voyager shortly before launch. When Voyager 2 completed Saturn successfully in 1981, and the spacecraft was still healthy, the extension to Uranus was approved. When Uranus went well in 1986, Neptune was approved. So the Grand Tour happened after all, one approval at a time, on hardware built for a mission half its size by people who had quietly kept the door open. That is worth remembering when you hear the mission described as visionary. It was, and the vision had to be smuggled past a budget process that had already said no once. Now the launches, and there is a detail in them that catches people out. Voyager 2 launched first, on August 20th of 1977. Voyager 1 launched second, on September 5th, 16 days later. The numbering is not a mistake, and it is not arbitrary. Voyager 1 was placed on a faster trajectory and would arrive at Jupiter first, so it was named for the order of arrival rather than the order of departure. Both were launched on Titan IIIe Centaur rockets from Cape Canaveral. The 2 spacecraft are close to identical. Each weighs about 1,590 pounds. Each carries a high-gain antenna 12 feet across, which is the dish you see in every photograph and which has to stay pointed at Earth for the mission to function at all. Each carries 3 radioisotope thermoelectric generators, which are the power source and which are Section 6, and each carries a golden record, which is Section 8. You should know what a gravity assist actually buys, in numbers, because it is easy to hear it as a small optimization. Voyager 2 arrived at Jupiter, traveling at around 22,000 miles per hour, relative to the Sun, and left at around 55,000. Jupiter more than doubled its speed without a single second of engine burn. Saturn added more. Uranus added more again. Without those assists, reaching Neptune would have required an amount of propellant no rocket then or now could lift. With them, the entire journey from Earth to Neptune was accomplished on the launch vehicle, plus a series of small trajectory corrections. The total propellant used for course adjustments across the whole mission is a modest quantity of hydrazine, most of which is still on board. So the answer to how a 1970s rocket reached 4 outer planets is that it did not. It reached Jupiter, and the planets did the rest. Now the trajectories, because the 2 spacecraft made different bargains and it determined everything that followed. Voyager 2 was aimed at the full tour. Jupiter, then Saturn, then Uranus, then Neptune. That path required accepting a slower route and a longer flight, and it required every encounter to work. because a failure at Jupiter would end the possibility of reaching the rest. Voyager 1 was aimed at Jupiter and Saturn, with a specific additional target at Saturn, the moon Titan. Titan was, at that point, the only moon in the solar system known to have a substantial atmosphere, and it was considered scientifically important enough to justify a close pass. But the geometry of that pass had a cost, and the cost was permanent. Flying close to Titan required Voyager 1 to be deflected sharply out of the plane the planet's orbit in. After Saturn, it would be heading upward, out of the flat disk of the solar system, and there was no possibility of it reaching Uranus or Neptune afterward, so the decision was made deliberately and in full knowledge. Voyager 1 would get Titan, and then leave the planetary system entirely. Voyager 2 would get the other two planets. That is why Voyager 1 is further out today despite launching second, and why it is travelling at a steeper angle. It was thrown upward and out at Saturn in 1980 and has been climbing away from the plane of the solar system ever since. Both launches had problems, which is worth knowing because the mission is usually remembered as flawless. Voyager 2's launch went off correctly, but once in space, the spacecraft's onboard computer detected what it interpreted as a fault and began switching to backup systems. It also failed to deploy the boom carrying the science instruments on schedule. Then, more seriously, a fault in the attitude control system was diagnosed. The spacecraft was working, but the confidence in it dropped enough that Voyager 1's launch sequence was reviewed. Voyager 1 then had a genuine hardware failure during ascent. The Centaur upper stage detected a problem and burned longer than planned to compensate, using nearly all its reserve. It made orbit and made the trajectory with about 3.5 seconds of fuel remaining. 3.5 seconds on the vehicle carrying the spacecraft that would fly for the next 49 years. Voyager 2 also lost its primary radio receiver in 1978, 7 months after launch, and the backup had a failed component that left it able to lock onto only a very narrow frequency band. Every command sent to Voyager 2 since 1978 has had to be transmitted at a precisely calculated frequency, adjusted for the Doppler shift caused by the spacecraft's motion and by the Earth's. That has been true for 48 years. Every single command. One more thing about the design, and it is the reason both spacecraft are still alive. They were built to survive Jupiter. Jupiter has a magnetic field far stronger than Earth's, and a radiation environment inside it that is genuinely extreme. The dose a spacecraft receives passing close to Jupiter can be 1,000 times what would kill a person. So the Voyagers were hardened. Sensitive electronics were wrapped in shielding. Critical components were selected for radiation tolerance, and redundancy was built in throughout. Voyager 1 received a dose at Jupiter estimated at around 3 times what it had been designed for, and survived. Some instruments were affected. The spacecraft kept working. That over-engineering, done for one encounter in 1979, is a large part of why the hardware is still functioning in interstellar space 49 years later. Nobody designed it to last this long. They designed it to survive Jupiter, and the margin they built in for that has been spending itself down slowly ever since. One more thing about that Titan decision, because it is the most consequential trade in the mission, and it deserves a fair account. The choice was not made casually, and it was argued about. Giving up 2 planets that no spacecraft had ever visited for one close pass at one moon is a large thing to give up. The reasoning was that Titan was the only moon known to have a thick atmosphere, that an atmosphere is where interesting chemistry happens, and that Voyager 2 would probably get Uranus and Neptune anyway if it kept working. That second part is the key. The Titan trade was only acceptable because there was a second spacecraft. If Voyager 2 had failed at Jupiter, Voyager 1 would have thrown away humanity's only chance at 2 planets for an orange ball. It did not fail. The bet paid. But you should notice what the bet actually was, because it is easy to read this history as a series of triumphs, and it was a series of gambles that happened to come off. One last thing about the design philosophy, because it explains something you will notice in every photograph of the spacecraft. Voyager looks cluttered. There are booms sticking out at odd angles, a dish that seems too large for the body, and instruments mounted on a platform that swivels. Every one of those choices is about interference. The magnetometers had to be 43 feet from the spacecraft because the spacecraft's own electronics produce a magnetic field strong enough to swamp what the instrument is trying to measure. The generators had to be on their own boom because they emit radiation that would degrade the instruments. The scan platform swivels because the antenna has to stay pointed at Earth while the cameras look somewhere else. So the awkward shape is not aesthetic indifference. It is a set of physical separations, each one solving a specific contamination problem, and the result is a machine that could only exist in an environment with no wind and no gravity to fight. That is the second section. The mission exists because Gary Flandreau noticed in 1965 that the 4 outer planets were about to arrange themselves in a pattern that recurs every 176 years. Voyager 2 launched first, and Voyager 1 was named for arriving first. Voyager 1 traded Uranus and Neptune for a close pass at Titan, which threw it up out of the plane of the solar system, and it has been climbing ever since. Before 1979, the outer solar system was 4 points of light and a great deal of guessing. Everything anybody knew about Jupiter, Saturn, Uranus and Neptune had been assembled from telescopes at a distance of hundreds of millions of miles. The moons were dots, the rings were a smear, nobody had seen a surface. Then 2 spacecraft went past in 12 years and returned the pictures, and almost every textbook had to be rewritten. That is the third section, and it is the part of the mission the spacecraft were actually built for. Everything since has been an extension. You should know how sparse the prior knowledge was, because it is difficult to reconstruct now. Before 1979, the best images of Jupiter came from ground telescopes and from the 2 Pioneer probes that had flown past in 1973 and 74. The Pioneers carried a spin-scan imaging system rather than a camera, and the results were low resolution and hard to interpret. Jupiter's moons were known to exist and known roughly how big they were. Nothing about their surfaces was known at all. Whether they were cratered, icy, cracked, smooth, active or dead was completely open. Saturn's rings were known to be made of particles from Maxwell's work in 1859 and Keeler's measurement in 1895, and the internal structure was unknown. Uranus and Neptune were disks a few arc-seconds across. So the honest state of knowledge going in was 4 objects with measured masses, measured orbits, rough compositions, and essentially no observed detail. Jupiter first. Voyager 1 arrived in March of 1979, Voyager 2 in July. You should have a sense of what the images actually looked like when they arrived, because the process was nothing like receiving a photograph today. Voyager's cameras are Vidicon tubes, not digital sensors in the modern sense. Each image is 800 by 800 pixels, 8 bits deep, which is 640,000 pixels total. A single image took about 48 seconds to record onto tape, and then had to be transmitted at a data rate that, at Jupiter, was around 115,000 bits per second. That sounds slow, and it was the fastest the mission ever achieved. By Neptune, it was down to about 21,000. Today, Voyager transmits at 160 bits per second. That is roughly 1,000th of the slowest home internet connection anybody has used. At that rate, transmitting one of those old images would take about 90 minutes, and there is no camera left to take one. The planet itself was expected to be interesting, and it was. The Great Red Spot was resolved into a storm system with structure and circulation, rotating counterclockwise with a period of about 6 days. But the results that mattered came from the moons, and one of them was found by a navigation engineer 3 days after the encounter. Her name is Linda Morabito, and she was working on optical navigation images, which are photographs taken of a moon against the background stars to fix the spacecraft's position precisely. Routine work. She increased the brightness on an image of Io to bring out faint stars, and there was a bulge on the edge of the disk, a crescent-shaped cloud, about 160 miles high, sticking out past the limb of the moon. It was a volcanic plume, caught mid-eruption. Nobody had ever observed active volcanism anywhere except Earth. Io turned out to have hundreds of active volcanoes, driven not by internal radioactive heat, but by tidal flexing from Jupiter's gravity, and it is now known as the most volcanically active body in the solar system. The prediction that this might be happening had been published in a paper 3 days before Voyager arrived, by Stanton Peele and colleagues on theoretical grounds. It is one of the closest calls between a prediction and a confirmation in the history of planetary science. You should know how close a call that was, because the story is usually told as though the discovery was inevitable. The plume Morabito found is on the very edge of the frame. It is faint, and it only became visible because she deliberately overexposed the image to bring out background stars for navigation. Nobody was looking for volcanoes. She was working out where the spacecraft was. Her own account is that she assumed at first it was another moon behind Io, and that it took a while to rule that out. If she had not brightened that particular frame, the plume would have sat in an archive. Other images did contain evidence, and it would have been found eventually, but the discovery as it happened turned on one person doing routine work carefully and then not dismissing something odd. That is worth holding whenever you hear that a spacecraft discovered something. Spacecraft return data. People find things in it. Europa was the second result. Voyager returned images of a surface almost entirely without craters, covered instead in long dark lines crossing an ice shell. A surface without craters is a young surface, because craters accumulate over time, and something has to be erasing them. The interpretation that emerged, and which has strengthened ever since, is a liquid water ocean beneath the ice. Every subsequent argument about life in the outer solar system traces back to those images. Voyager also found that Jupiter has rings, which had not been suspected. They are faint, made of dust, and were detected only because the imaging team took a long exposure looking back towards the sun to check. There is one more Jupiter result that gets less attention and is worth your time, because it is the closest anybody has come to watching a physical process nobody expected. The 4 large moons of Jupiter had been points of light since Galileo found them in 1610. Voyager resolved them into worlds, and the striking thing was how different they are from each other. Io is volcanic and yellow and has no craters at all, because the surface is being repaved continuously. Europa is smooth white ice with dark cracks and almost no craters either, for a different reason. Ganymede, the largest moon in the solar system, larger than the planet Mercury, has ancient dark terrain alongside younger grooved terrain, meaning something resurfaced parts of it and then stopped. Callisto is the opposite extreme. It is saturated with craters. Every part of the surface has been hit so many times that new impacts erase old ones, which is what a surface looks like when nothing has happened to it for 4 billion years. 4 moons orbiting the same planet, formed at the same time from the same material, and they range from the most geologically active body in the solar system to one of the most completely dead. The reason is distance from Jupiter, and therefore tidal heating. Io is closest and gets flexed hardest. Callisto is furthest and gets almost nothing. That gradient, visible across 4 objects in one system, is one of the cleanest demonstrations of tidal heating anywhere, and nobody had seen it before 1979. Saturn next. Voyager 1 arrived in November of 1980, Voyager 2 in August of 1981. The rings, seen from a few 100,000 miles instead of 800 million, stopped being a handful of bands and resolved into thousands of individual ringlets with sharp edges, gaps, waves, and braided strands. One of the scientists described the images as looking like a phonograph record. They also found dark radial streaks appearing and disappearing across the rings, called spokes, which are still not fully explained 46 years later. If you have ever seen a photograph of Saturn's rings that looks like a phonograph record, that is a Voyager image or a descendant of one. The visual vocabulary everybody now carries for that planet was produced in about 9 months across 2 flybys, and then Titan, which was the whole reason Voyager 1 gave up 2 planets. The close pass returned an orange sphere with no visible surface whatsoever. The atmosphere is thick, it is mostly nitrogen, and it is completely opaque at the wavelengths Voyager's cameras used. That is worth sitting with, because it is the one genuine disappointment in the mission. The encounter that cost Uranus and Neptune returned a featureless orange ball. What it did establish was the composition and pressure of the atmosphere, which is about 1.5 times Earth's at the surface, and that was enough to make Titan a target for everything that followed. The Cassini mission and the Huygens probe that landed there in 2005 exist in part because Voyager showed there was something worth going back for. So the trade was not wasted, it just did not look like a win at the time. There is a detail about the Saturn encounter that had consequences nobody wanted, and it involves Voyager 2 rather than 1. As Voyager 2 swung past Saturn in August of 1981, the scan platform, the swiveling mount carrying the cameras, jammed. It stuck during the most important hours of the encounter and stayed stuck for days. A significant number of planned observations were lost. The cause was traced to a lubrication problem in the gear train, aggravated by the platform having been slewed rapidly and repeatedly during the flyby. The platform was eventually freed, and it worked at Uranus and Neptune, but only under a rule that it would never again be moved at high speed. That is worth knowing because the entire Uranus and Neptune campaign, the only close observations of 2 planets that humanity has, was conducted with a camera mount that had already failed once and was being operated gingerly. Then Voyager 2 continued alone. Saturn returned 2 more things worth naming before we leave it. The first is the moon count. Before Voyager, Saturn had about a dozen known moons. Voyager found several more, and more importantly, found that some of them are doing structural work. Small bodies sitting inside gaps in the rings, or orbiting just outside them, holding the ring edges in place by gravity. Those got called shepherd moons, and the concept did not exist before those images. The second is a moon that looks wrong. Iapetus had been known since 1671 to be far brighter on one side than the other, bright enough that it can be seen on one side of its orbit and almost disappears on the other. Voyager photographed it and confirmed the 2 hemispheres really are different, one about as reflective as snow, and the other about as dark as tar. Voyager could not explain why. That took until the Cassini mission decades later, and the answer involves dark material sweeping onto the leading face and then changing the local temperature enough to drive ice off it. That pattern repeats through this whole mission. Voyager finds the thing. Somebody else explains it 20 or 30 years afterward, using the Voyager images as the starting point. Uranus in January of 1986. Nothing had ever been there. The planet came back as a nearly featureless pale blue-green disk, which was itself informative, and the encounter established that Uranus is tipped over on its side, orbiting with its axis pointing almost at the Sun. You should know how hard that encounter was, because Uranus is dim. Sunlight there is about 1/400th of what it is here, so every image required long exposures, and the spacecraft was moving fast enough that a long exposure smears. The solution was to rotate the entire spacecraft slowly during each exposure to track the target. which had never been attempted and which required rewriting the onboard software from Earth 2 billion miles away before arrival. 10 new moons were found. Miranda, one of the previously known ones, turned out to have a surface that looks assembled from mismatched pieces, including a cliff estimated at over 12 miles high, which would be the tallest known anywhere in the solar system. That encounter has a piece of context that is easy to forget. Voyager 2 reached Uranus on January 24th of 1986. The Challenger accident happened 4 days later, and coverage of the first visit to a planet nobody had ever seen disappeared from the news almost immediately. Uranus produced one more result that took decades to appreciate, and it is about the magnetic field. Every planet with a magnetic field has it roughly aligned with the rotation axis. Earth's magnetic poles are close to its geographic ones, off by about 11 degrees. Uranus's field is tilted about 59 degrees from its rotation axis, and it is offset from the center of the planet, emerging from a point roughly a third of the way out toward the surface. Nothing predicted that, and it is still not fully explained. The leading idea involves the field being generated in a shallow layer of electrically conducting fluid, rather than in a deep core, which would be a different mechanism from Earth's dynamo entirely. Then Voyager reached Neptune and found the same thing again. Tilted about 47 degrees, and also offset. 2 planets, both with fields that behave in a way no other planet does. 1 measurement is an oddity, 2 is a category. That result is one of the strongest arguments for going back, and it has been sitting unresolved since 1989. Neptune in August of 1989, and it is the last planetary encounter either spacecraft made. Neptune was expected to be quiet. It receives about 1,000th of the sunlight Earth does, and there was no obvious energy source to drive weather. It has the fastest winds measured anywhere in the solar system, reaching around 1,200 miles per hour. It had a storm system comparable in structure to Jupiter's Great Red Spot, which was named the Great Dark Spot, and which had vanished by the time Hubble looked again 5 years later. And Triton, its largest moon, turned out to be one of the strangest objects in the system. It orbits backwards, which means it was almost certainly captured rather than formed in place. Its surface is around -391 degrees Fahrenheit, among the coldest measured anywhere, and Voyager photographed plumes erupting from it, making it one of the few worlds known to be geologically active. Then it was over. Neptune was the last planet, and after August of 1989, there was nothing ahead of either spacecraft but distance. There is one more image from this period, and it is not a science result. On February 14th of 1990, at a distance of about 3.7 billion miles, Voyager 1 turned its camera back toward the Sun and photographed the planets it had left behind. The idea had been pushed for years by Carl Sagan, and it was resisted, partly because pointing the camera near the Sun risked damaging it, and partly because the scientific value was close to zero. The camera had to be commanded carefully. Pointing an imaging system near the Sun can destroy it, so the sequence was designed to photograph the planets while keeping the Sun itself just outside the field, and it was executed as the last thing the cameras ever did. 60 frames were taken. 6 of them contained planets. Mercury was too close to the Sun to attempt. Mars was lost in scattered light, and Pluto was too faint. Earth occupies less than a single pixel in the resulting frame. It sits in a band of scattered sunlight, which is an artifact of the optics rather than anything real. Sagan's argument for taking it had nothing to do with science, and he said so. He wanted a photograph of Earth from the outside, taken from far enough away that the planet was demonstrably small, because he thought seeing it would do something that being told it would not. Whether that worked is not something anybody can measure, and I would be careful about claiming it did. What is true is that the image has been reproduced continuously for 36 years, and that most people who know anything about Voyager know that photograph before they know anything else about the mission. You have almost certainly seen it. It is a dark frame with colored bands of scattered light across it, and a single pale dot that you would not find without being told where to look. The cameras were switched off permanently shortly afterward, to save power and because there was nothing left to photograph. There is a practical detail worth adding. The cameras were not just powered down. The software that operates them was eventually overwritten, and the engineers who wrote it have largely retired or died. So even if there were power to spare, the capability to take another photograph no longer exists. The pale blue dot is the last image either Voyager will ever produce, and that was settled not by a decision, but by attrition. There is a fact about those 4 encounters that is worth stating plainly, because it explains why this mission still matters scientifically, rather than only historically. Not once, in 40 and 37 years respectively. Everything humanity knows about either planet from close range comes from a single spacecraft flying past at speed over a few days in 1986 and 1989. Every image you have ever seen of Uranus or Neptune from nearby is a Voyager 2 image. Every measurement of their magnetic fields, their internal structure, their moons and rings, comes from those 2 encounters. A Uranus orbiter has been recommended as the highest priority large mission for the next decade by the planetary science community. If it is funded and flies, it arrives in the 2040s, which means that for something like 60 years, the entire close-range record of 2 of the 8 planets will have come from one spacecraft that is still, tonight, flying. That is the 3rd section. In 12 years, 2 spacecraft visited 4 planets and returned the first close images ever taken of any of them. Active volcanoes were found on Io 3 days after being predicted. Europa's ice shell suggested an ocean. Titan turned out to be opaque. Uranus was visited 4 days before Challenger. Neptune had 1,200 mile-per-hour winds and a moon orbiting backwards. And then the cameras were turned off and the mission became something else. Nobody noticed when it happened. The most reported milestone in the history of unmanned spaceflight, the day Voyager 1 crossed out of the sun's bubble and into interstellar space, went by without anybody on Earth being aware of it. The date was August 25th of 2012, and it was established more than a year afterward, working backwards through data that had already been sitting in an archive. That is the 4th section. And if you have only ever seen the headline version, the real story is considerably better. Start with what the boundary is, because the word heliopause gets used a great deal and explained rarely. The sun does not only emit light, it emits a continuous stream of charged particles in every direction, called the solar wind, moving at hundreds of thousands of miles per hour. That wind blows a bubble. It pushes outward against the thin gas that fills the space between stars, and it clears a cavity for itself, and everything inside that cavity is under the sun's influence, rather than the galaxies. The bubble is called the heliosphere. Its outer wall, where the solar wind finally loses the argument and stops, is the heliopause. That is the boundary Voyager crossed. Not the edge of the solar system, the edge of the sun's wind. You have a version of that bubble much closer to home, which makes the shape easier to hold. The Earth has a magnetic field that pushes back against the solar wind and clears a cavity around this planet. The wind cannot get in, and where it is stopped, there is a boundary. The heliosphere is the same arrangement 1 level up. The sun's wind pushes against the interstellar gas and clears a cavity around the whole solar system. So you are inside 2 nested bubbles. Earth's magnetic cavity sits inside the sun's wind cavity, which sits inside the galaxy. Voyager left the outer one in 2012. It is the only object that ever has. Now the problem of detecting it, which is where the story gets interesting. The obvious way to know you have crossed is to measure the plasma directly. Inside the bubble, the gas is hot, fast and thin. Outside it is cooler, slower and considerably denser. Point an instrument at it and read the difference. Voyager 1 could not do that. Its plasma science instrument had failed in 1980. It had been dead for 32 years by the time the spacecraft reached the boundary, and there was no way to fix it. So the crossing had to be established indirectly, from instruments that were not designed for the job. That failure is worth a moment on its own, because it changed the mission permanently, and it happened for a mundane reason. The plasma science instrument on Voyager 1 stopped returning usable data in 1980. It was not damaged by radiation or by an impact. A component failed. At the time, it did not seem like a large loss. The spacecraft had finished at Saturn. The primary mission was over, and interstellar space was a theoretical destination decades away. 32 years later, that one dead instrument was the difference between measuring the most important boundary crossing in the mission's history directly and having to reconstruct it from proxies over 13 months. Voyager 2's equivalent instrument still works, which is why its crossing in 2018 was clean. So the two spacecraft, built identically, had completely different experiences of the same event, because one component failed on one of them in 1980. 3 signatures were expected. The first was the count of charged particles coming from the Sun, which should collapse once the spacecraft left the region those particles occupy. The second was the count of galactic cosmic rays arriving from outside, which should jump, because the heliosphere partly shields the inside from them. The third was the direction of the magnetic field, which was expected to change as the spacecraft moved from the Sun's field into the galaxies. Notice what you are being asked to accept there. 2 of those 3 are counts of particles, and a count going up or down could be caused by several things. Only the magnetic field direction was considered decisive on its own. In August of 2012, the first 2 happened, sharply and within days of each other. Solar particles dropped away almost to nothing. Cosmic rays jumped to the highest levels ever recorded by the spacecraft. The third did not happen. The magnetic field direction stayed essentially where it had been. That is why nobody announced anything. 2 out of 3 signatures pointed one way, and the third, which theory said should be the clearest, refused to cooperate. Some researchers argued the spacecraft had crossed. Others argued it was in a transitional region nobody had predicted. The disagreement ran for a year in the literature, and it was genuine. What settled it came from an instrument that measures something else entirely, and from a piece of luck. The plasma wave subsystem does not measure the density of the gas around the spacecraft directly. It listens for oscillations in it. When plasma is disturbed, it rings at a frequency that depends on how dense it is. In the same way, the note from a struck object depends on its size. The trouble is that plasma has to be disturbed before it rings, and out there very little disturbs it. Then in March of 2013, the Sun helped. A large outburst that had left the Sun about a year earlier finally reached Voyager, hit the gas around it, and made it ring. Don Gurnett and his team at the University of Iowa read the frequency and calculated the density. The gas around Voyager 1 was about 40 times denser than the solar wind should be. That number is only consistent with interstellar space. Working backwards through an earlier, weaker oscillation recorded in the data, they placed the crossing at August 25th of 2012. The announcement came in September of 2013, 13 months after the event. Now the part that explains why the third signature failed, because it turned out to be informative rather than an error. The expectation had been that the galaxy's magnetic field would be oriented differently from the Sun's, so crossing between them would produce an obvious change in direction. What appears to have happened is that the interstellar field near the boundary has been draped and pushed around by the heliosphere itself, like water flowing around a rock, so that in the region Voyager passed through the 2 fields are nearly parallel. The prediction was not wrong about the physics, it was wrong about the local geometry, and the only way to find that out was to fly a spacecraft through it. There was an earlier boundary too, and Voyager crossed it years before, which is part of why the 2012 reporting got confused. The solar wind leaves the sun at supersonic speed. As it pushes outward and meets resistance from the interstellar gas, it has to slow down, and it does that abruptly at a shock front called the termination shock. That is not the edge of the bubble. It is where the wind inside the bubble stops going supersonic. Past it there is a turbulent region called the heliosheath, where the slowed wind piles up before the actual boundary. Voyager 1 crossed the termination shock in December of 2004 at about 94 astronomical units. Voyager 2 crossed it in August of 2007 at about 84. Then both spent years crossing the heliosheath. Voyager 1 took about 8 years to get from the termination shock to the heliopause. So the structure from the inside out is supersonic solar wind, then the termination shock, then the turbulent heliosheath, then the heliopause, then interstellar space. 3 layers and 2 boundaries, and coverage of both crossings tended to describe whichever one had just happened as leaving the solar system. You can see why the public account got muddled. What you cannot see from the coverage is that the different distances at which the 2 spacecraft crossed, 94 against 84 and later 121 against 119, are themselves a measurement. The bubble is not a sphere. It is squashed on one side because the whole solar system is moving through the interstellar gas, and the bubble has a leading edge and a trailing one. Voyager 2 crossed 6 years later, on November 5th of 2018, at about 119 astronomical units. That crossing was cleaner in one important way. Voyager 2's plasma instrument still works. It measured the density change directly, in real time, rather than inferring it a year later from a ringing sound. The 2 crossings happened at slightly different distances, which tells you the boundary is not a perfect sphere, and comparing them gave the first measurement of its shape. Now, what interstellar space is actually like, since Voyager is the only thing that has ever reported from inside it? You would probably assume it is emptier than the solar system. It is not. It is denser. Inside the heliosphere, the solar wind is thin because it has been blown outward from a single point and spread across an enormous volume. Typical densities out of Voyager's distance were around 1 atom in every few cubic inches. Outside, in the interstellar medium, the density is roughly 40 times higher. Still an extraordinary vacuum by any earthly standard, still emptier than anything a laboratory can produce, and still denser than the bubble. The temperature is also higher, in a way that needs care. The gas outside registers at tens of thousands of degrees. That sounds lethal, and it is not, because temperature measures how fast individual particles are moving, and there are so few of them that they carry almost no heat. A thermometer out there would read extremely cold, because it would radiate away far more energy than the sparse fast particles could deliver. That distinction between temperature and heat is one of the few genuinely counterintuitive things in this video, and it is worth holding. The gas is hot, and the environment is freezing, and both statements are correct. Voyager also found that the magnetic field out there is stronger than expected, and that cosmic rays arrive at rates roughly double what they were inside the bubble, which is a direct measurement of how much shielding the heliosphere provides. That last number matters beyond Voyager. It is the best available data on the radiation environment any future long-duration mission would face. So what should you take from 2012? Voyager 1 left the region of space controlled by the sun's wind. That is real, it is measured, and it is the first time anything built by humans has done it. It did not leave the solar system, and the next section is about how much of the solar system is still ahead of it. There is a lesson buried in this section that goes beyond Voyager, and it is the reason I wanted to tell it in this much detail. You will often hear a scientific result described as though somebody looked at an instrument and read off an answer. Almost nothing works like that. What actually happened here is that an instrument failed 32 years before the measurement mattered. 2 proxies gave a partial answer. A third contradicted it. The field argued for a year, and the question was finally settled by an unrelated instrument catching a chance event and a team having the idea to interpret it that way. Then the answer had to be dated backwards through an archive. That is what the sentence, "Voyager crossed into interstellar space in 2012, actually contains. And the confidence in the final number is high, precisely because it survived a year of people trying to break it. One last thing about that boundary, and it is about what it means for us rather than for Voyager. The heliosphere is a shield. Section 4 established that cosmic ray levels roughly double once you leave it, which means the sun's wind is deflecting about half of what would otherwise reach the planets. The whole solar system is inside that shield, and it moves. As the sun travels around the galaxy, it passes through regions of denser and thinner interstellar gas, and the bubble expands and contracts in response. There is a serious body of work asking whether passing through a dense cloud could compress the heliosphere enough to leave Earth exposed, and whether that has happened in the past. The evidence is tentative, and I would not overstate it. What is established is that the shield is not fixed, that Voyager has now measured the outside of it directly, and that this is the only dataset anybody has for calibrating any of that work. A mission launched to photograph Jupiter is now the sole source of ground truth for questions about the long-term radiation history of this planet. That is the fourth section. The crossing happened on August 25th of 2012, and nobody knew for 13 months. The instrument that should have measured it had been dead since 1980. 2 of 3 expected signatures appeared, and the third did not, because the galaxy's magnetic field turned out to be draped around the heliosphere in a way nobody had predicted. It was finally settled when a solar outburst made the surrounding gas ring, and the note it produced was 40 times denser than the solar wind could explain. If you were asked where the solar system ends, you would probably say Pluto, or Neptune, or possibly the point Voyager crossed in 2012. All 3 are reasonable, and all 3 are wrong by an enormous margin. That is the 5th section, and it is the one that makes the title of tonight's video literally true. There are 3 different edges, they are at wildly different distances, and the confusion between them is where nearly every misleading headline about Voyager comes from. The first edge is the planets. Neptune at 30 astronomical units. That is the boundary most people carry, and it is the edge of the region with large objects in it, which is a reasonable thing to care about, and is not the edge of anything else. The second edge is the heliopause, at around 120 astronomical units. That is the wall of the sun's wind, from section 4, and it is what Voyager crossed. The third edge is gravitational, and it is the real one. The sun's gravity does not stop at the heliopause. It does not stop anywhere in particular. It weakens with distance and eventually becomes too feeble to hold on to anything against the pull of neighboring stars, and where that happens is the actual limit of the sun's territory. That limit sits at somewhere around 100,000 astronomical units. Take those 3 numbers together, 30, then 120, then 100,000. Voyager is at 170. It has crossed the second boundary, and it is at less than 1/500th of the way to the third. You can test whether that third number is doing real work by asking what it is based on, because a boundary defined by gravity sounds vague, and it is not. Every object orbiting the sun is being pulled by the sun, and also, faintly, by every other star in the galaxy. Close in, the sun wins overwhelmingly. Far out, the difference narrows. The distance at which the sun's pull on an object drops to roughly the level of the combined pull from everything else is calculable, and it comes out at something like 2 light years, which is around 125,000 astronomical units. That is the sun's actual gravitational domain, and objects can and do orbit out there. They orbit slowly. A body at 100,000 astronomical units takes something like 30 million years to go around once. So the outer solar system is not a vague fading away. It is a region with a defined edge or a specific balance tips. containing objects on orbits that take longer than the existence of the human genus to complete. Now, what is out there? Because that region is not empty, and it has a name. The Oort cloud is a shell of icy bodies surrounding the entire solar system in every direction, not a flat disk like the planets. Estimates put the number of objects larger than about a mile across somewhere in the trillions. It has never been directly observed. Not one object has been imaged in place out there. The evidence for it is indirect, and it is good. Long-period comets, the ones that appear once and take thousands of years to return, arrive from every direction rather than from the plane of the planets, and their orbits trace back to distances of tens of thousands of astronomical units. Something has to be supplying them. The idea was worked out by the Dutch astronomer Jan Oort in 1950. From exactly that reasoning, estimates for where it begins vary, and I want to give you the range rather than a false number. The inner edge is usually placed somewhere between 2,000 and 5,000 astronomical units. The outer edge runs to somewhere around 100,000, and some estimates push it further. There is a region between the planets and the Oort cloud that I have skipped, and should not, because it is the one part of the outer solar system that has actually been visited. The Kuiper belt is a flattened ring of icy bodies beyond Neptune, running from about 30 to about 50 astronomical units. Pluto is in it. So are hundreds of thousands of catalogued objects larger than about 60 miles across. That is a real, mapped, observed region, and New Horizons flew through it, photographing Pluto in 2015, and then a smaller object called Arrokoth in 2019. Voyager passed through the Kuiper belt in the 1980s and 90s without noticing, because by then the cameras were off, and because the belt is so sparse that passing through it involves encountering nothing. Then there is a gap. From about 50 astronomical units out to the inner edge of the Oort cloud at a few thousand, there is very little that anybody has found, except for a handful of objects that do not fit anywhere, and one of them is worth naming. Sedna was discovered in 2003. Its orbit takes it from about 76 astronomical units at closest approach out to something like 900 at its furthest, on a circuit lasting roughly 11,000 years. Nothing explains an orbit like that easily. It never comes close enough to Neptune to have been thrown out there by it, and it goes too far out to have formed where it is. Objects like Sedna are the main observational evidence that something exists between the Kuiper belt and the Oort cloud, and there are only a few of them known. So the honest map of the outer solar system is planets to 30, Kuiper belt to 50, then a poorly understood region with a handful of strange objects in it, then a hypothetical shell of trillions of bodies that nobody has ever directly seen, extending most of the way to the next star. Voyager is at 170, in the poorly understood part. There is a consequence of the Oort cloud shape that is worth stating, because it changes how you should think about the solar system as a whole. The planets are a disk. Everything you have ever seen drawn as a diagram of the solar system is a flat arrangement, because the planets all orbit close to the same plane, inherited from the disk of gas they formed in. The Oort cloud is not a disk, it is a sphere, surrounding everything in every direction. So the true shape of the solar system is not a flat plate. It is a vast ball with a very thin disk at the center, and the disk, the part with all the planets in it, occupies a fraction of the volume too small to draw. If the Oort cloud were the size of a stadium, the planetary system would be smaller than a coin at the middle of the pitch, which means that when Voyager climbed up out of the plane of the planets at Saturn in 1980, it was not leaving the solar system's shape, it was leaving the coin. Now the timings, which are the numbers that matter for tonight. At 38,000 miles per hour, Voyager 1 reaches the inner edge of the Oort cloud in roughly 300 years. 300 years from now is further into the future than the United States has existed into the past. Passing all the way through and out the other side takes something on the order of 30,000 years. 30,000 years ago, the last ice age was near its peak. There were no cities, No agriculture, no writing. Humans were painting on cave walls in southern Europe. That is the length of the departure Voyager is currently 49 years into. So when the coverage in 2012 said Voyager had left the solar system, what had actually happened was that it had completed the first 1500th of the journey out. I want to be fair to the people who wrote those headlines, because the mistake is more forgivable than it looks. The heliopause is a real boundary, and crossing it was a real first. It is also the only edge out there that a spacecraft can detect. There is nothing to feel at the gravitational limit. No wall, no signature, no instrument reading. It is a place where an accounting of forces tips over. So the heliopause is the only edge that produces a moment, and a moment is what a headline needs. The larger boundary is real, and it will pass unremarked, because there will be nothing left to remark with. There is a question you might have by now, which is why nobody has ever seen an Oort cloud object if there are trillions of them. The answer is brightness. Those objects are small, dark, and extremely far away, and they produce no light of their own. Sunlight reaching an object at 10,000 astronomical units is 100 million times weaker than sunlight at Earth, and then whatever reflects has to travel all the way back. The result is beyond the reach of any telescope built or planned. What can be seen is an Oort cloud object that has fallen inward. When one is disturbed by a passing star or by the galaxy's own tide and drops toward the sun, it heats up, throws off gas and dust, and becomes a comet with a tail bright enough to see from a garden. So every long-period comet you have ever heard of is a former Oort cloud object, temporarily visible because it left. Hale-Bopp in 1997 is the best-known recent one. Its orbital period is around 2,500 years. That is a short one by the standards of that population. The cloud itself remains a population inferred entirely from its escapees. One more thing worth knowing about this region, because it changes what the emptiness actually contains. The gas between the stars is not nothing. It is extremely thin, at roughly 1 atom in every cubic inch or so, which is better than any vacuum ever produced in a laboratory. But over billions of miles, even that adds up, and Voyager is now measuring it directly. The plasma wave instrument, the one that settled the crossing, has since detected a faint, persistent hum. It is the sound of the interstellar medium itself, ringing continuously at very low level, and it was found in 2021 by Stella Koch-Hocker, then a graduate student at Cornell, going back through Voyager data looking for exactly that. So the spacecraft is not just traveling through interstellar space, it is listening to it, and what it hears is a steady tone. One more comparison, because the 3 edges are easier to hold as a ratio than as 3 separate numbers. If the distance to Neptune is 1 step, then the heliopause is 4 steps, and the outer edge of the Sun's gravity is more than 3,000 steps. Walk 1 pace for Neptune, 4 paces to where Voyager crossed, then keep walking for 1.5 miles. That is the shape of it, and it is why the 2012 headline was not so much wrong as answering a different question from the one people thought it answered. There is a question underneath all of this that is worth asking directly, which is whether the word solar system even has a single correct definition. It does not, and that is the source of the confusion rather than any mistake by anybody. If you define it as the region containing the planets, it ends at Neptune. If you define it as the region dominated by the sun's wind, it ends at the heliopause. If you define it as everything gravitationally bound to the sun, it ends around 100,000 astronomical units. All 3 are used by professionals in different contexts, and each is correct for its purpose. What went wrong in 2012 is that a spacecraft crossed one boundary and the coverage reported it as crossing a different one, and almost nobody noticed because most people did not know there was more than one. So the useful thing to carry is not a corrected number. It is the awareness that the phrase "leaving the solar system" does not have a single meaning, and that anybody using it should say which edge they mean. That is the 5th section. There are 3 edges to the solar system, at 30, 120, and 100,000 astronomical units. Voyager crossed the second one and is at 170. Reaching the inner edge of the Oort cloud takes 300 years, and passing beyond it takes about 30,000. The gravitational boundary is the real edge of the Sun's territory, and nothing will ever detect crossing it, because there is nothing there to detect. 18 days ago, a team at the Jet Propulsion Laboratory did something to Voyager 2 that they had one attempt at and no way to undo. They called it the Big Bang. It happened on August 4th of this year. It involved switching off several powered devices simultaneously and substituting lower power alternatives in the same operation, and it bought the spacecraft at least another year of science. If it had gone wrong, there was no recovery. There is no engineer within 11 billion miles and no possibility of physical repair. The command sequence had to be correct when it left Earth. That is the 6th section, and it is about the slow arithmetic that is going to end this mission. Start with where the power comes from, because it is not solar and it never was. At Jupiter, sunlight is about 1/27th as strong as at Earth. At Neptune, it is about 1/900th. Solar panels were never an option for the outer solar system in the 1970s and are still marginal today. So each Voyager carries 3 radioisotope thermoelectric generators, usually shortened to RTGs. The principle is simple, and it has no moving parts, which is the entire reason it works for 50 years. Each generator contains plutonium-238, which is radioactive and decays steadily. As it decays, it produces heat continuously, whether anybody wants it to or not. Surround that heat source with thermocouples, which are junctions of 2 different materials that produce a small voltage when one side is hotter than the other, and the heat becomes electricity. No pumps, no turbines, no fuel to run out, just a hot lump and a temperature difference. At launch, the 3 generators together produced about 470 watts. That is worth pausing on. 470 watts is roughly what a small household appliance draws. Everything Voyager has ever done, every photograph of Jupiter, every measurement in interstellar space, every transmission across 15 billion miles, was done on less power than a domestic toaster. There is a detail about that plutonium worth knowing, because it explains why nothing like Voyager is easy to build today. The isotope used is plutonium-238, and it is not the material used in weapons. That is plutonium-239, a different isotope with different properties. 238 is essentially useless for anything except producing heat, which is exactly what makes it ideal here. It has to be manufactured. It does not occur naturally in any useful quantity, and producing it requires a reactor and a chemical processing chain. The United States stopped making it in the late 1980s. For roughly 30 years, every deep space mission requiring one of these generators was drawing down a finite stockpile, supplemented by purchases from Russia. Production restarted at Oak Ridge National Laboratory in the 2010s, at a rate measured in a few pounds per year, against a goal of somewhat more. So the supply is constrained, and it is one of the real reasons missions to the outer solar system are rare. It is not only cost, and not only distance. There is a limited amount of the one substance that lets a spacecraft work out there at all. Now the decline, which has 2 causes rather than one. The first is the plutonium. It has a half-life of about 88 years, so the heat output falls by around 0.8% annually. That part is unavoidable physics. The second is the thermocouples. They degrade over time, and their efficiency falls faster than the fuel does. Together, the 2 effects cost the spacecraft about 4 watts every year. 4 watts a year, from a starting point of 470, for 49 years. The generators today produce a little over 200 watts, and by the early 2030s there will not be enough to run a transmitter and an instrument at the same time. That is the whole of the end game. Not a failure, not an accident, not a collision. An arithmetic problem that has been running since 1977 and has one outcome. You can check that arithmetic against something in your own house, because the decay rate is the same physics that dates archaeological material. Half-life means the time for half the atoms to decay. For plutonium-238, it is about 88 years. So of the fuel loaded in 1977, roughly 2/3 remains today. By the 2060s, half of it will be gone. That alone would not end the mission. A spacecraft on 2/3 of its original heat could still work. What compounds it is the thermocouples. They have been sitting in a temperature gradient for 49 years, and their conversion efficiency has fallen substantially. That degradation is the larger part of the loss, which is a slightly annoying fact. The nuclear fuel is holding up better than the conversion hardware, and the mission ends because of the part that turns heat into electricity rather than the part that makes the heat. Now what has been switched off? Because the list is how you read the situation. Each Voyager launched with 10 science instruments. The cameras went first in 1990, after the last photographs. Others followed over the decades as the budget of watts tightened. This year has been the heaviest. On February 25th of 2026, the cosmic ray subsystem on Voyager 1 was switched off. On March 24th, the low-energy charged particle instrument on Voyager 1 was switched off. That was the 8th of the original 10 to be deactivated on that spacecraft. 3 instruments turned off permanently in 8 weeks, on hardware that has been running for nearly half a century, because there were not enough watts to keep them. What remains on Voyager 1 is the magnetometer and the plasma wave subsystem. On Voyager 2, those two plus the cosmic ray subsystem, which is what the Big Bang was performed to protect. It is worth understanding how old the technology is, because you are almost certainly carrying more computing power right now than the entire spacecraft contains. Voyager has 3 pairs of computers. Their total memory across all 6 is about 70 kilobytes. A single photograph on the phone in your pocket is several thousand kilobytes. A text message is a few. The entire operating memory of the most distant object humans have ever built would not hold one modern image. The data is recorded on magnetic tape, physical tape on reels that winds and rewinds. That is how it stored the Jupiter and Saturn images before transmitting them, and the mechanism is still functional. The software is written in assembly language for processors that no longer exist commercially, and in a NASA-specific language called heliopause. Nobody has learned either of those in a working context for decades. That creates a problem you might not anticipate. When something goes wrong, the people who can diagnose it are the people who built it, and most of them are retired or dead. The mission has dealt with this by keeping paper records, by bringing former engineers back as consultants, and in some cases by digging through boxes of documentation stored in a basement because the answer to a question about a 1970s design decision was never digitized. That is not a colorful anecdote. It is the actual operational situation. The oldest working spacecraft is maintained partly through archaeology. If you want a sense of what that means practically, consider that the spacecraft cannot be updated the way you update anything else you own. There is no patch, no download, no rollback. A software change is a sequence of commands transmitted over hours, executed once, with a 2-day round trip to find out whether it worked, and no way to undo it if it did not. Every change is permanent on arrival. Now the decision-making, which is the part I find hardest to think about clearly. Every one of those shutdowns is a choice made by a small team, weighing which measurement to lose in order to keep the others alive a little longer. The instruments are not broken, they work. They are switched off because the alternative is that everything switches off sooner. The team doing this is small, it operates on a modest budget, and several of the people involved have worked on this mission for decades. Some of the engineers who wrote the original software have been consulted in retirement because the systems predate almost everybody currently in the building. Voyager runs on computers with less memory than a greetings card that plays a tune. Commands are written in a language nobody has used professionally since the 1970s, The documentation is partly on paper, and the work continues, 1 watt at a time. The other half of keeping this mission alive is not on the spacecraft at all. It is on the ground, and it is a piece of infrastructure most people have never heard of. The Deep Space Network is 3 complexes of radio dishes, placed roughly 1/3 of the way around the planet from each other. Goldstone in California, Madrid in Spain, and Canberra in Australia. 3 sites at those spacings means that as the Earth turns, at least one of them can always see any given point in the sky. There is no moment when a distant spacecraft is unreachable. Each complex has a dish 230 feet across, along with several smaller ones. Voyager needs the big ones. The signal is too faint for anything else. And there is a complication that constrains the whole mission. Because of where Voyager 2 is in the sky, deep in the southern celestial hemisphere, it can only be reached from Canberra. Not Madrid, not Goldstone. One dish on one continent is the entire link to one of the 2 spacecraft. When that dish was taken offline for upgrades in 2020 and 2021, Voyager 2 could receive nothing for 11 months. Commands could not be sent. The spacecraft transmitted, and the ground could listen, and nobody could talk back. The network is also oversubscribed. It supports dozens of missions, and Voyager competes for time with spacecraft returning far more data. What Voyager gets is scheduled sessions rather than continuous coverage. So the picture is a spacecraft losing 4 watts a year and a ground system that has to be shared, and a team allocating both. There is a piece of that work from 2023 worth including, because it shows what the margins now look like. Voyager 2 was running out of power and the mission faced switching off an instrument. Engineers found a reserve, a small amount of power that had been held back as a safety buffer, protecting the spacecraft's instruments from a voltage fluctuation that had never occurred. They decided the risk of using it was acceptable. They tapped the safety margin and kept an instrument running. That is the level things are at, spending the emergency reserve to buy another year. There is a second constraint that is not about electricity at all, and it will probably end the mission before the power does. The thrusters. Voyager has to keep its antenna pointed at Earth. It does that with small hydrazine thrusters that fire in brief pulses whenever the spacecraft drifts off alignment. Each firing is tiny. There have been hundreds of thousands of them. The problem is not running out of fuel, although that will eventually happen. It is that the fuel lines are slowly clogging. Each firing deposits a small residue inside the propellant inlet tubes, and after 49 years of pulses the tubes are narrowing. Engineers have managed this by switching between thruster sets. Each spacecraft has a primary set, a backup set, and a set of thrusters originally intended only for trajectory corrections during the planetary encounters. Those last ones had not been fired since 1980, when they were brought back into use. They worked, thrusters dormant for 37 years, in an environment near absolute zero, fired on command. The current planning assumes the tubes clog to the point of failure somewhere in the 2030s. Whether that arrives before or after the power runs out is genuinely uncertain, and the team is managing both clocks at once. Then this month, the Big Bang. The same reasoning, executed on a larger scale, on a spacecraft nearly 50 years old with no possibility of a second attempt. It worked. There is a comparison that puts the 200 watts in perspective, and I find it clarifying. A single incandescent light bulb of the old kind draws about 60 watts. A modern laptop under load might draw 65. A kettle draws around 3000. Voyager, today, runs on about the power of 3 old light bulbs. And out of that, it has to heat the fuel lines, run the computers, operate 2 instruments, and transmit a signal across 15 billion miles. By the early 2030s, it will be down to roughly 2 bulbs, and that is not enough. You could power what remains of the most distant object humans have ever built from a wall socket without noticing it on your bill. That is the resource the entire remaining mission is competing over. That is the sixth section. Voyager runs on plutonium heat converted to electricity. It started with 470 watts and loses about 4 a year, and it now has a little over 200. 8 of 10 instruments on Voyager 1 are off. 3 of them switched off this year. On August 4th of this year, JPL performed a one-attempt power reconfiguration on Voyager 2 and bought at least another year. The mission does not end because something breaks. It ends because the arithmetic runs out. There will be a last transmission, and nobody will know it was the last one at the time. That is the seventh section, and it is the one I think about most, because the ending of this mission has a specific shape that is different from how anything else ends. You will probably be alive for it, which is not something you can say about most of the numbers in tonight's video. Everything else here is measured in centuries or in tens of thousands of years. This one is in single digits. Start with the timeline, and I will give you the range rather than a single confident year. The current published expectation is that the Voyagers will run out of usable power somewhere around the end of this decade. The goal the engineers are working toward is keeping at least one instrument alive on each spacecraft into the 2030s. Estimates cluster around 2030 for the point where science stops, with efforts like the Big Bang from the last section pushing at the edges of that. But there is a distinction inside the ending that matters, and it is worth being precise about. Losing the instruments is not the same as losing the spacecraft. An instrument draws power, so does the transmitter. As the budget shrinks, the instruments go first, one at a time, because a spacecraft that can still talk is worth more than one carrying a working sensor it cannot report from. So the sequence is instruments off, one by one, until none are left. Then the spacecraft is still there, still transmitting engineering data, telling the ground how it is and nothing else. A signal that says only that a signal is still possible. And then that goes too. The transmitter needs power, and the antenna needs to stay pointed at Earth. Pointing requires the attitude control thrusters to fire occasionally, and those need hydrazine, and there is a finite amount of hydrazine remaining. When either the power or the propellant runs out, the antenna drifts off Earth and the signal stops. There is an order to the shutdown that is worth having, because it is not the order you might guess. You might assume the science comes last, since it is the point of the mission. It goes first. The reasoning is that a spacecraft with a working transmitter and no instruments can still be tracked, still be commanded, and still be recovered if something changes. A spacecraft with a working instrument and no transmitter is gone, so the transmitter is protected at the expense of everything else, down to the final watts. The very last thing to go will be the ability to say anything at all, and by then there will have been nothing to say for a while. Now the reason nobody will know which transmission was the last. The Deep Space Network does not listen to Voyager continuously. It is a shared resource, 3 complexes around the world, tracking dozens of missions. Voyager gets scheduled sessions. So a gap in the data is normal. It happens constantly. When the signal fails to arrive, the first assumption is a scheduling issue, or a ground station problem, or a spacecraft fault that might be recoverable. Voyager has gone quiet before and come back, and the 2 most recent cases are worth telling properly, because they show what operating this spacecraft now actually involves. The first was Voyager 2, in July of 2023. A routine set of commands was sent, and one of them contained an error that tilted the spacecraft's antenna about 2 degrees away from Earth. 2 degrees does not sound like much. At 11 billion miles, it is everything. The signal stopped. There was a scheduled automatic correction built into the spacecraft, a routine that reorients it toward Earth several times a year, and the next one was months away. The plan, initially, was to wait. Instead, the team tried something. Using the largest dish in the Deep Space Network at Canberra in Australia, they transmitted a command at the highest power available, on the reasoning that even pointed 2 degrees off, The very edge of Voyager's antenna sensitivity might catch enough of it. They described it afterward as shouting. It took about 18.5 hours for the shout to arrive, and another 18.5 for any reply. The reply came. The spacecraft had heard, had turned, and was pointed at Earth again. The second was Voyager 1, starting in November of 2023, and it lasted much longer. The spacecraft was transmitting, and the signal was arriving on schedule, and what it contained was meaningless. A repeating pattern with no data in it, the equivalent of a dial tone where a voice should be. The problem was traced over several months to the flight data subsystem, one of the onboard computers, and eventually to a single chip containing part of the system's memory. About 3% of that memory had stopped working, and the corrupted section happened to hold code the spacecraft needed in order to package data for transmission. There is no way to replace a chip at 15 billion miles. What the engineers did instead was find unused space elsewhere in the memory, break the affected code into pieces small enough to fit in the gaps, rewrite it so the relocated pieces still referenced each other correctly, and send the whole thing up. The first section was transmitted in April of 2024. It worked. The spacecraft started returning readable engineering data for the first time in 5 months. Over the following weeks, the rest was moved, and the science instruments came back one by one. Those 2 episodes happened within a year of each other, on spacecraft that were 46 years old, and both were recovered. That is the context for what happens at the end. When the signal stops for good, it will look exactly like these did at first. The difference is that this time the fix will not work, and it will take a while for anybody to be sure of that. In 2023, a wrong command pointed Voyager 2's antenna 2 degrees off Earth, and contact was lost for about 2 weeks, until a very high-powered signal from Canberra managed to command it back. In 2023 and 2024, Voyager 1 returned nonsense for months after a memory fault, and engineers eventually diagnosed a single failed chip and worked around it from 15 billion miles away. So when the signal stops for the last time, the first reaction will be to try to get it back, and the team will keep trying. And after some period of silence, somebody will conclude that this time it is over. The last transmission will be identified retroactively, from the logs, the way the 2012 crossing was. There is a question you might be asking, which is why not simply turn everything off and save the power for later? It does not work, and the reason is heat. Voyager is in an environment around -450 degrees Fahrenheit. The spacecraft stays functional because the plutonium generators produce waste heat and because the electronics themselves run warm. Fuel lines, in particular, have to stay above the temperature at which hydrazine freezes. Turn a system off, and that section of the spacecraft starts to cool. Let it get cold enough and components crack, seals fail, and lines block permanently. So some of the power is not doing science and is not optional. It is keeping the machine from freezing solid. That constrains everything. Each shutdown decision has to account for what the removed heat does to whatever was near it, and in several cases heaters have had to be turned off to save power, while accepting that a component will now run colder than it was designed for. The team has repeatedly found that parts survive temperatures well below their rated minimums. That is not good engineering practice. It is what is available. Now the part I want to state carefully, because it is easy to sentimentalize, and the facts are better than the sentiment. The signal Voyager sends is extraordinarily faint. By the time it reaches Earth, the power arriving at the antenna is measured in units so small they are difficult to convey. It is routinely described as less than 1/1000,000,000th of a watt. Receiving it at all requires dish antennas, 230 feet across, cooled receivers, and knowing exactly where to point and what frequency to expect. The Deep Space Network was built partly for this, and it has been maintained for 50 years partly for this. And when Voyager stops, there will be a set of capabilities on Earth that were kept alive to hear something that is no longer speaking. You can put a number on how faint it is if you want one that makes the point. A digital watch battery, over its whole life, delivers more energy than the entire Voyager signal has delivered to Earth across 49 years of transmission. The total energy collected by every antenna from every Voyager transmission ever received adds up to less than the energy of a snowflake landing. That is not a figure of speech. It is roughly the arithmetic, and it is why the receivers have to be cryogenically cooled and why the dishes have to be that large. Everything anybody knows about the outer planets from close range and everything anybody knows about interstellar space from inside it arrived as less energy than a snowflake hitting the ground. Then what? The spacecraft does not stop. That is the thing worth holding on to. The transmitter goes silent and the object continues at 38,000 miles per hour on exactly the trajectory it is on now, because there is nothing out there to slow it down. No air, no friction, nothing to fall into. It becomes, in that moment, a piece of debris, an inert assembly of aluminum, gold, plutonium and wire on a permanent path out of the solar system, with nobody aboard and nothing left to report. And it stays that way for a very long time, which is section 9. There is a specific asymmetry in the ending that I want to name because it is unusual. Almost everything that ends does so in a way somebody witnesses. A building comes down, a company closes, a person dies, and there is a moment and people present for it. Voyager's ending happens 15 billion miles away, in a place nobody can observe, at a time nobody will identify until afterward, and the only evidence will be the absence of something. You cannot watch it. There will be no image. The spacecraft will not do anything at the end that it was not doing before. It simply stops being audible, and the silence is indistinguishable from a scheduling gap until enough of them accumulate. That means there is no last picture of Voyager, no final signal worth broadcasting, no moment to mark. Whatever ceremony there is will be organized afterward, around a date somebody worked out from a log file. I find that appropriate rather than sad. It matches the rest of the mission, which has consistently done extraordinary things quietly and been noticed later. One more thing about the ending, and it is a practical point rather than an emotional one. There is an argument, made seriously, that the Voyagers should be kept alive as long as possible even after the last instrument dies, purely to maintain the tracking capability and the institutional knowledge. The counter-argument is money. The mission costs a few $1 million a year to operate, which is small by spaceflight standards and is not nothing, and it competes with missions that are returning more science. That tension is real, and it is being managed year by year. What has happened repeatedly is that the team has found another way to buy time, and the mission has been extended again, and the deadline has moved. It has moved many times. It will not move forever. If you want a date to hold this one loosely. The current best expectation is that both spacecraft go quiet somewhere between 2030 and the mid-2030s, with the exact year depending on how much more the engineers can find. That estimate has moved before. It was going to be the 2010s, then 2020, then 2025. Every time, somebody found another what. So the responsible thing to say is not a year. It is that the window is now measured in single digits of years rather than decades, and that if you want to be able to say you were alive while it was still talking, you already can. That is the 7th section. The power runs out around the end of this decade. The instruments go first, then the engineering signal, and then the spacecraft goes quiet with the antenna drifting off Earth. Nobody will know which transmission was the last until they go back through the logs. The signal arriving now is less than a billionth of a watt, and the network built to hear it will outlive the thing it was listening to. Bolted to the side of each spacecraft is a gold-plated copper disc, 12 inches across, and it will outlast everything else on board by an amount of time that is difficult to write down. That is the 8th section, and it is about the one component of Voyager designed with no expectation of ever being used. Start with how it happened, because the timeline is absurd. The decision to include a message was made late. A committee was assembled and chaired by Carl Sagan, and the group had roughly 6 weeks to decide what should represent Earth and to physically produce it. 6 weeks to choose what a species says about itself. The team included Sagan, his wife at the time Linda Salzman Sagan, the writer Anne Druyan as creative director, the astronomer Frank Drake, the artist John Lomberg, and the journalist Timothy Ferris as producer. What they made is a phonograph record. That was not a nostalgic choice. In 1977, a grooved disc was the most durable way anybody knew to store analog information for a long period without power. A groove is a physical shape. It does not degrade the way a magnetic or electronic medium does, and reading it requires no technology more advanced than a needle and a steady hand. The record is copper, plated in gold to resist corrosion, and sealed in an aluminum cover. If you are wondering why a record rather than something denser, the answer is that every alternative available in 1977 was worse. Magnetic tape degrades and needs a specific machine to read. Punched materials store very little. Film fades and requires chemistry to develop. Anything electronic requires power, and there would be none. A groove requires no power, no chemistry, and no compatible hardware beyond a needle. The information is the physical shape of the surface, and physical shapes last. That reasoning still holds. If you were asked today to store information for 1 billion years with no power, the answer would still be to cut it into something durable, and you would probably still choose metal. Now what is on it? 115 images, encoded as analog signals in the audio. Photographs of Earth, of human anatomy, of a fetus, of people eating, of a supermarket, of the structures of DNA, of mathematical definitions, greetings spoken in 55 languages, from Akkadian, which has not been spoken in about 4,000 years, to modern Chinese dialects. The English greeting was recorded by Sagan's 6-year-old son Nick, who said hello from the children of planet Earth. A sequence called the sounds of Earth: thunder, rain, surf, wind, a heartbeat, footsteps, a kiss, a mother speaking to her child, a chimpanzee, a tractor, a train, Morse code, a rocket launch, and 90 minutes of music. The selection is worth listing partly because the choices are strange, and partly because the argument over them was fierce. Bach appears 3 times, more than anybody else. Beethoven's Fifth, Mozart's Magic Flute, Stravinsky's Rite of Spring, Louis Armstrong playing Melancholy Blues, Chuck Berry's Johnny B. Good, Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, which is a man humming over a slide guitar, and which several members of the committee argued was the most important thing on the disc. Music from Java, Senegal, Australia, Peru, Bulgaria, Japan, India, Mexico, the Navajo Nation, the Solomon Islands. There is a well-known story that the committee wanted a Beatles track and could not clear the rights. The details of who blocked it are contested, so I will say only that the Beatles are not on the record and that the reasons involved rights rather than taste. Anne Druyan also had her brainwaves, heart and eye movements recorded as an hour of electrical activity, compressed into an audio segment. She has said since that during the recording she was thinking about the history of ideas and about having fallen in love with Sagan days earlier. She and Sagan married in 1981. So there is, on a disc leaving the solar system, an hour of one person's nervous system while she was thinking about being in love. A few of the choices deserve more than a listing, because the arguments behind them tell you what the committee thought it was doing. Dark Was the Night, Cold Was the Ground is the one that keeps getting singled out. Blind Willie Johnson recorded it in 1927. There are no words. It is a man humming over a slide guitar, and Johnson himself died in poverty in 1945 after his house burnt down and he slept in the ruins. Andrew Yan has said the reason it is on the record is that it expresses something about loneliness and endurance that does not require language to understand, which is the only quality that matters for an audience with no shared language. Johnny B. Good caused an argument. Some members of the committee thought rock and roll was adolescent and did not belong. Carl Sagan's reported answer was that there are a lot of adolescents on the planet. The greetings in 55 languages were recorded quickly, without much coordination, and it shows. The speakers were largely people who happened to be available at Cornell University, and each was told roughly what to say rather than given a script. Some are formal, some are casual. One, in Amoy, translates roughly as an invitation to come and eat if you have time. There is also a printed message from Kurt Waldheim, then Secretary General of the United Nations, and one from Jimmy Carter, then President. Carter's includes the line that this is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings. And there is one thing that is on the record by accident, of the era rather than by choice. The images include a photograph of a nursing mother, a diagram of human reproductive anatomy, and a picture of a man and a woman. The nude photographs originally intended were rejected by NASA, so the human figures appear as line drawings while a great deal else is photographic. That decision was made in 1977 by an agency worried about public reaction, and the consequence is permanent for as long as the object exists. There is an audio segment on the record that people tend to skip past in the listings, and it is worth naming because it is the oldest thing on there. Among the sounds of Earth is a sequence intended to represent the planet's history: volcanoes, earthquakes, wind, rain, surf, then the sounds of living things, then the sounds of people, then the sounds of machines. It is arranged chronologically. It starts with geology and ends with a rocket. So the record contains, in about 12 minutes, a compressed account of 4.5 billion years, assembled by people who had 6 weeks and had to decide what mattered. Now the cover, which is the part that has to work hardest. The aluminum case is engraved with instructions, and the instructions have to be understandable by someone with no shared language, no shared culture, and no shared biology. There is a diagram of the record and the stylus in position, showing how to play it. There is a number written in binary, giving the correct rotation speed, expressed in terms of a fundamental transition of the hydrogen atom, which is the same everywhere in the universe, and is therefore the only unit that can be assumed. There is a diagram showing how to reconstruct the images from the signal, and there is a pulsar map, 14 lines radiating from a point, each pointing toward a pulsar, with the pulsar's rotation period written in binary along the line. Pulsars spin at extremely precise rates that change slowly and predictably, so the map functions as both a position and a date. Anybody who found it could work out where the sun is and roughly when the record was made. Frank Drake designed that map. A version of it had flown earlier on the Pioneer plaques. There is a criticism of the record worth raising, because it is fair and it usually gets left out. The committee was 6 people, all American, working in 6 weeks in 1977. What they produced is presented as a portrait of Earth, and it is a portrait of Earth as seen from one country, at one moment, by a small group with particular tastes. The music selection leans heavily on Western classical. The images skew toward the technological and the scientific. The greetings were recorded from whoever was available at one university. There is no famine, no war, no disease, no poverty in the images. That was deliberate, and Sagan said so, but you should know it is a curated and flattering account rather than a complete one. None of that makes it a failure. 6 weeks is 6 weeks, and the alternative was sending nothing. But if you ever see it described as humanity's message to the stars, it is worth remembering that humanity did not choose it. 6 people did, quickly, and then it left. Now the honest part, because this is where the coverage usually goes soft. The chance of the golden record ever being found and played is effectively zero. Voyager is not going anywhere in particular. It is not aimed at a star system. Space is overwhelmingly empty, and an object 12 feet across drifting between stars is not going to be intercepted by accident. The people who made it knew that. Sagan said as much repeatedly. The record was never a serious attempt at communication. What it is, and what he argued at the time, is a statement about the people who sent it. A civilization that assembles a considered account of itself and attaches it to an object leaving forever is saying something about its own view of itself, and the audience for that statement is here. There is a detail on the cover that is easy to miss, and is arguably the cleverest thing on the whole object. In one corner there is a small circle of electroplated uranium-238. Uranium-238 decays with a half-life of about 4.5 billion years. Anybody finding the record and measuring how much of it has decayed into its daughter products can calculate how long ago the sample was pure. It is a clock, not a symbolic one, a physical clock built into the casing, readable by anybody with the chemistry to measure isotope ratios, accurate over billions of years. Between that and the pulsar map, the object tells a finder both where it came from and when it left, using nothing but physics that works the same everywhere. There is one thing on the record that was added at the last moment and is not on any manifest. The metal master was being prepared, and somebody at the plant etched a short message into the run-out area, the blank space near the center where a needle would finish. It reads, "To the makers of music, all worlds, all times." It was not authorized. Whoever did it was not part of the committee. By the time it was noticed, the disc had been produced, and the decision was made to leave it. So there is an unsigned line, added by an anonymous technician in 1977, currently 15 billion miles from the person who wrote it, and it will still be legible when the Earth is uninhabitable. Now the durability, which is the number that ends this section. The record is protected from the main thing that erodes surfaces in space, which is micrometeoroid impact, by its aluminum cover and by the near total emptiness it is traveling through. Estimates for how long the engraved information would remain legible run into the hundreds of millions of years. Some analyses put it at 1 billion or more. The Sun will render Earth uninhabitable in roughly 1 billion years as it continues to brighten. The Sun itself becomes a red giant in about 5 billion. So the reasonable statement is this: the golden record will very likely still be readable long after the surface of this planet has stopped being able to support the species that made it. It is the most durable object humans have ever produced, and it was assembled in 6 weeks by a committee working to a deadline. The record has had an odd second life down here, and it is worth a moment because it is the part you can actually access. For decades, the contents were difficult to obtain. The images were published in a book, the audio existed in archives, and there was no straightforward way for an ordinary person to hear what had been sent. In 2017, a crowd-funded project produced a physical vinyl reissue of the complete record, working from the original masters, with the images printed as a book. It raised over $1 million from people who wanted a copy of a thing whose only other copies are 11 and 15 billion miles away. NASA has since made the audio and images freely available online, so you can listen to it tonight if you want. The greetings, the thunder, the whale song, the Bach, the blind Willie Johnson. I would recommend the Johnson track specifically, and I would recommend knowing while you listen that 2 copies of it are traveling out of the solar system at 38,000 miles an hour and will still be doing so when the Sun has finished with this planet. That is the 8th section. 2 gold-plated copper discs are traveling out of the solar system carrying 115 images, greetings in 55 languages, the sounds of Earth, 90 minutes of music, and an hour of one woman's brainwaves. The cover explains how to play it using the hydrogen atom as the unit and a pulsar map as the address. It will almost certainly never be found. Everybody involved knew that, and it will remain legible for longer than the Earth remains habitable. Everything from here is arithmetic, because nothing else happens. That is the 9th section, and it covers the period from the last transmission to the end of the Sun. It is the longest section of tonight's video by duration and the emptiest by events. Start with the near term, if 3 centuries counts as near. Around the year 2300, give or take, Voyager 1 reaches the inner edge of the Oort cloud. Nothing marks it. There is no boundary to cross in any physical sense, and at that point the spacecraft has been silent for roughly 270 years. Then it spends about 30,000 years passing through. I want to be careful about what that means, because the word cloud produces the wrong image entirely. The Oort cloud contains something in the order of trillions of objects, which sounds crowded. It is spread across a shell tens of thousands of astronomical units in radius, which is an almost unimaginable volume. Work out the density, and the typical separation between neighboring objects comes out at something like tens of millions of miles. So Voyager will pass through the most populated region of the outer solar system, and the probability of coming near anything is negligible. It will not hit a comet. It will very likely not pass within a distance where anything would be visible. 30,000 years of nothing, and then it is out. It is worth being clear about what will actually be happening to the spacecraft during that stretch, because the answer is almost nothing, and that is itself remarkable. No air, so no corrosion and no weathering. No sunlight worth the name, so no ultraviolet degradation of surfaces. No gravity gradients strong enough to stress the structure. No temperature cycling, because there is nothing to heat it up during a day, and no day. The only meaningful erosion is from occasional impacts with interstellar dust grains, which are microscopic and extremely rare, and from cosmic rays slowly damaging materials at the atomic level. Both processes are so slow that estimates for how long the structure survives are measured in billions of years rather than millions. So the spacecraft does not decay in any way you would recognize. It just goes cold, and stays cold, and keeps going. Then the encounter, which is the closest thing to an event in the rest of this story. In roughly 40,000 years, Voyager 1 passes within about 1.6 light-years of a star called Gliese 445, which is currently about 17 light-years away in the constellation Camelopardalis. That star is moving toward us. In 40,000 years, it will be considerably closer to the Sun than it is now, and Voyager's path and its path will bring them into relative proximity. 1.6 light-years is not close. It is about 40% of the distance from here to Proxima Centauri. Nothing would be visible to anybody standing on a planet there, if there were a planet and if anybody were standing on it. Voyager 2 has its own near-miss, passing within about 1.7 light-years of a star called Ross 248 in roughly 40,000 years. Those are the only 2 approaches to anything in the entire future of both spacecraft that anybody has bothered to calculate. You should know how those encounter figures are calculated, because it is not obvious and the method is unusually recent. Predicting where a star will be in 40,000 years requires knowing not just where it is now, but how fast it is moving and in what direction, in 3 dimensions. That is a hard measurement. Sideways motion across the sky is slow and takes decades of observation to detect, and motion toward or away requires spectroscopy. The Gaia spacecraft, which operated from 2013 to early 2025, measured the positions, distances and motions of nearly 2 billion stars. Before Gaia, the future encounter list for the Voyagers was rough. After it, the trajectories of nearby stars are known well enough that the calculation is meaningful. So the statement that Voyager passes 1.6 light-years from Gliese 445 in 40,000 years is a recent result, resting on a survey that finished last year, and it will be refined further as the Gaia data is fully analysed. That is a small thing, and I like it. The spacecraft left in 1977, and we are still improving our understanding of where it is going. You might reasonably want to know whether either spacecraft could ever hit anything, and the honest answer is that the probability is not zero, but it is close enough that nobody calculates it seriously. The interstellar medium contains dust grains, and Voyager is running into them continuously. They are microscopic. Each impact removes an amount of material too small to matter, and over billions of years, those impacts are the main thing that will eventually wear the surfaces down. Larger objects are the question, and the answer is that interstellar space is so empty that the nearest sizable object to Voyager at any given moment is likely to be light years away. To put that in perspective, if you scattered a handful of grains of sand across the volume of the Earth, the spacing would be crowded compared to the density of objects between stars. So nothing stops it, nothing catches it, nothing is in the way. That emptiness is why the projections hold. On Earth, predicting where anything will be in 30,000 years is impossible because too much interacts with it. Out there, almost nothing does. Now the long term, and this is where the numbers stop being comparable to anything. After the Oort cloud, both Voyagers are in orbit around the center of the galaxy, not around the Sun. The Sun's hold is gone and they are independent objects, circling the galactic center the way every other star in this region does. One orbit of the galaxy takes roughly 225 million years. The Voyagers will complete that orbit, then another, then another. There is no mechanism to stop them. The interstellar medium is thin enough that drag is negligible over these timescales. Nothing decays their orbit. Nothing intercepts them. Estimates for how long the physical structure survives run into the billions of years, limited mainly by erosion from cosmic rays and from the occasional dust grain impact, which over that span slowly wears the surfaces down. Now the comparison that makes those numbers land. The Sun will begin to expand into a red giant in about 5 billion years. Earth will be sterilized well before that, in roughly 1 billion. As the Sun's brightening drives away the oceans, the Voyagers will still be in flight. Whatever happens to this planet, to the species that built them, to the institutions and the languages and the records, two objects assembled in California in the 1970s will still be moving through the galaxy in orbits that take 250 million years to complete, carrying an engraved account of where they came from. That is not a poetic claim. It is a consequence of there being nothing out there to stop them. There is a way to hold 225 million years that helps, because the number is otherwise just a lot of zeros. The last time the Sun was at its current position in its orbit around the galaxy, the first dinosaurs were appearing. One galactic orbit ago, there were no birds, no flowers, and no mammals to speak of. The Sun has completed roughly 20 of those orbits in its lifetime. Voyager will complete its first about 225 million years from now, and by then this planet's surface will be unrecognizable, and the spacecraft will be an unchanged piece of aluminum traveling at exactly the speed it is traveling tonight. Nothing in the intervening time affects it. That is the strange part. Everything that will happen down here, all of it, happens while nothing at all happens to the object. Now the honest caveat, because these projections have real uncertainty in them. Trajectories over 40,000 years are calculated from current positions and velocities and the known gravitational field of the galaxy. That calculation is good, but it is not perfect, and small errors compound over that length of time. The Gliese 445 encounter distance should be treated as an estimate with meaningful uncertainty rather than a precise figure. Over millions of years, the trajectory becomes genuinely unpredictable in detail, because a close pass by any unmapped object would change it, and there is no way to know about such objects in advance. So the correct statement is not that we know where Voyager will be in 1 billion years. It is that we know it will still be moving, and that nothing plausible stops it. There is a question people ask about the golden record that belongs in this section rather than the last one, which is whether anything could plausibly find it. Work through the geometry and the answer is close to no. Voyager is not aimed at a star. Its trajectory takes it into a region of the galaxy, not toward a destination. The nearest it comes to anything in the next 40,000 years is 1.6 light years, which is roughly 10 trillion miles. For something to find it, that something would have to detect a 12-foot object, unpowered, unlit, radiating nothing at interstellar distance, and then intercept it. Detecting it would be harder than detecting a planet, and we can barely do that. So the honest position is that the record is a message with no plausible recipient, launched by people who said at the time that it had no plausible recipient, and its value was never in being received. One more thing to close this section, and it is the fact I find most useful for holding the scale. Voyager 1 has been flying for 49 years and has covered about 0.0027 light years. To cover a single light year at its current speed takes about 17,000 years. To reach the distance of the nearest star, if it were aimed at one, which it is not, would take about 73,000 years. The spacecraft will be dead for 72,950 of them. There are two other objects on similar trajectories, and it is worth knowing they exist, because Voyager is not alone out there. Pioneer 10 and Pioneer 11 launched in 1972 and 1973 before the Voyagers, and were the first spacecraft to cross the asteroid belt and reach Jupiter. Both are on escape trajectories out of the solar system. Both stopped transmitting long ago. Pioneer 10 sent its last signal in January of 2003. Pioneer 11 went silent in 1995. They are still going. Two inert objects, drifting outward, carrying engraved aluminum plaques designed by Carl Sagan and Frank Drake that show a man, a woman, the solar system, and a pulsar map. The plaques are the direct predecessor of the Golden Record. New Horizons, which photographed Pluto, is the fifth object on an escape trajectory. It is still transmitting and will continue into the 2040s. So the count is 5. 2 Pioneers, silent. 2 Voyagers, talking for now. 1 New Horizons, that is the entire population of human-made objects leaving the solar system, ever, and 4 of the 5 were launched before 1978. One more thing about that population of 5, because there is a detail that surprised me. They are not going the same way. Pioneer 10 is heading roughly toward the constellation Taurus. Pioneer 11 toward Aquila. Voyager 1 is climbing north out of the plane, toward Ophiuchus. Voyager 2 is heading south, toward Pavo. New Horizons is heading toward Sagittarius. 5 objects, 5 different directions, spreading outward from one point. None of those headings was chosen as a destination. Each is simply the direction the last gravity assist happened to leave the spacecraft pointing. So the pattern of human-made objects leaving the solar system is not a fleet aimed anywhere. It is a scatter determined by which planets each probe used and in what order, radiating out from a single star in 5 unrelated directions. That is the 9th section. Voyager reaches the inner Oort cloud in about 300 years and takes 30,000 to pass through it, encountering nothing. In roughly 40,000 years, it passes 1.6 light years from Gliese 445. After that, it orbits the center of the galaxy every 225 million years, indefinitely, and it will still be doing so after the Sun has destroyed the Earth. So what is actually out there? Not what it means. What it physically is. That is the 10th section, and it is an inventory. If you were somehow beside it tonight, this is what you would find. An aluminum framework about the size of a small car with a 12-foot dish antenna mounted on one end. A 10-sided bus containing the electronics. 3 booms extending outward, one carrying the instruments, one carrying the generators, one carrying the magnetometers, and running about 43 feet out to keep them away from the spacecraft's own magnetic interference. The dish is aluminum honeycomb, chosen because it is stiff and light and holds its shape without any structure behind it. It has to stay accurate to a fraction of an inch across 12 feet, because a warped dish scatters the signal. It has held that shape for 49 years through the temperature extremes of 4 planetary encounters and half a century in vacuum. Total mass at launch, about 1,590 pounds. About the weight of a small car, spread across a structure the size of one. Inside the bus, 3 computer systems, each duplicated for redundancy. Their combined memory is roughly 70 kilobytes. That is smaller than a single low-resolution photograph on any phone made in the last 15 years. Data is stored on an 8-track digital tape recorder, physical tape, wound and rewound, which on Voyager 1 has run for enough cycles to be equivalent to playing a cassette continuously for decades. The plutonium in the generators is still decaying and will continue to produce a diminishing trickle of heat for centuries after there is anything left to power. In 88 years, there will be half as much as today. In 880 years, about 1,000th. The gold-plated record on the side, which Section 8 covered, and the small amount of hydrazine, the last of it, for the thrusters that keep the antenna pointed until there is no longer any reason to point it. That is the object. That is the whole of it. There is one more item that is not on the manifest and is physically present, and it is the strangest thing in the inventory. Bolted to the record cover, and on the pioneer plaques before it, is information about where the object came from. But inside the spacecraft, in a more literal sense, is the material itself. The aluminum was mined on Earth. The gold on the record was mined on Earth. The plutonium was manufactured in a reactor in the United States. Every atom in the structure was assembled here, by people, out of material that came out of this planet's crust. In 1 billion years, when the surface of the Earth has changed beyond recognition, there will be a few hundred pounds of processed terrestrial matter traveling through the galaxy in a configuration that only a technological species could have produced. That is not a poetic framing. It is a description of what is out there. Refined metal, in shapes that do not occur naturally, moving on a trajectory that no natural process would produce. Now the thing I keep coming back to. Everything in that inventory was designed for a 4-year mission to 2 planets. The extended tour to Uranus and Neptune was an extension. The interstellar mission was an extension of the extension. Nobody in 1977 was designing hardware for 2026, because nobody imagined the hardware would be asked to do this. The margins that make it possible were put there for other reasons. Radiation hardening for Jupiter. Redundancy for reliability. A power source chosen because solar panels do not work past Mars. Add those together and you get, accidentally, a machine that lasts 50 years. There is one more thing in the inventory that is not hardware, and I think it is the part worth carrying. Every command Voyager has ever executed was written by somebody. Every trajectory correction, every instrument shutdown, every recovery from a fault was a decision made by a person and typed out and sent. Some of those people are dead. The mission has outlived a meaningful fraction of the people who built it, and it will outlive the rest. The current team is small, measured in a handful of engineers rather than a division. Several have worked on it for 30 or 40 years. When the signal stops, some of them will have spent their entire working lives on one spacecraft, and there will be nothing further to do. That is a real thing that is going to happen to real people within about 4 years, and it does not usually get mentioned alongside the numbers. You might reasonably ask why keep going at all. The instruments are nearly gone, the data rate is tiny, and the money could fund something newer. The answer the mission gives is that this is the only direct measurement of interstellar space anybody has. Everything else we know about the medium between stars is inferred from a distance. 2 objects are physically inside it, reporting what it is like, and when they stop there will be no replacement for decades at least. Nothing is currently planned or funded to go out there and do it again. There is one more question worth answering before the summary, because you may have been holding it for a while. Could we do it again? Could something be launched now that goes further, faster, and lasts longer? The honest answer is yes on 2 counts and no on the 3rd. Faster is achievable. A launch using a close pass by the sun, or a heavy launcher with a small payload, could beat 38,000 miles per hour by a meaningful margin. Concepts exist for probes reaching 2 or 3 times Voyager's speed. Further follows from faster, given time. Longer is the problem. The limit is the power source, and the plutonium supply is constrained for the reasons Section 6 covered. A mission designed to operate for 50 years in interstellar space needs a generator, and generators need fuel that exists in small quantities and is expensive to make. There is a concept called interstellar probe, studied in detail in recent years, which proposes a spacecraft designed from the start to reach 1,000 astronomical units and operate for 50 years. That is roughly 6 times Voyager's current distance. It is not funded. If it were approved tomorrow, it would launch in the 2030s and reach Voyager's current position around the 2060s. So the realistic answer is that nothing will overtake Voyager for decades, and the reason is not ambition. It is that the mission was launched at the right moment, with the right margins, and has been running ever since, and starting again from zero is slower than continuing. Now let me pull every thread we followed tonight together. Voyager 1 is 15.8 billion miles away, 170 astronomical units, moving at 38,000 miles per hour, and in November it becomes the first human object 1 full light day from Earth. It flew because Gary Flandreau noticed in 1965 that 4 planets were about to arrange themselves in a pattern that recurs every 176 years. Voyager 2 launched first. Voyager 1 traded Uranus and Neptune for a close pass at Titan and got thrown up out of the plane of the solar system. In 12 years, the 2 spacecraft returned the first close images of Jupiter, Saturn, Uranus, and Neptune. Active volcanoes on Io, spotted by a navigation engineer 3 days after a paper predicted them. An ice shell on Europa with an ocean underneath. Winds of 1,200 miles per hour on Neptune, and a moon orbiting backwards. On August 25th of 2012, Voyager 1 crossed the heliopause. Nobody knew for 13 months because the instrument that should have measured it had been dead since 1980, and it was finally settled when a solar outburst made the surrounding gas ring at a frequency only interstellar density could explain. That crossing was reported as leaving the solar system. The Sun's gravitational territory extends about 600 times further, 300 years to the inner Oort cloud, 30,000 to pass beyond it. The power source has been decaying since launch at about 4 watts a year, from 470 down to a little over 200. 8 of 10 instruments on Voyager 1 are off, 3 switched off this year. 18 days ago, JPL performed a 1-attempt power reconfiguration on Voyager 2 and bought another year. Around the end of this decade, the last instrument goes quiet, then the engineering signal, then the antenna drifts off Earth. Nobody will know which transmission was the last until they check the logs. And then an inert object continues at 38,000 miles per hour, passes 1.6 light years from Gliese 445 in 40,000 years, and orbits the center of the galaxy every 225 million years, carrying a gold-plated record that will stay legible for longer than this planet stays habitable. There is one comparison I want to leave you with before the bottom line, because it reframes the whole thing. Consider what was happening on Earth when this spacecraft left. 1977. There was no internet available to the public, no mobile phones, no personal computers in any meaningful number. Most photographs were on film and had to be developed. If you wanted to know something, you went to a library. Every piece of technology in your house is newer than Voyager. Every piece of technology you have ever owned is newer than Voyager. And the thing built before all of it, using components that would be considered primitive by any standard applied since, is the object that has gone the furthest and lasted the longest. That is not because the 1970s were better at engineering. It is because the mission was built with enormous margins for one dangerous encounter at Jupiter, and margins compound, which is a genuinely useful lesson, and it is not a nostalgic one. The reason Voyager is still alive is that somebody over-engineered it for a reason that had nothing to do with longevity, and then nobody was in a position to remove the excess. There is one thing I would push back on in how this mission usually gets talked about, and it is the word failure. You will sometimes see the ending framed as NASA abandoning Voyager, or as a funding decision killing it. That is not accurate, and it is unfair to the people involved. Nothing is being abandoned. The plutonium is decaying at a rate fixed by nuclear physics in 1977, and no budget changes it. The thermocouples degrade whether or not anybody watches. The fuel lines clog because thrusters have fired hundreds of thousands of times. A larger budget would buy more staff to squeeze out more watts, and that is roughly what has been happening for years. It does not buy new plutonium in a spacecraft 15 billion miles away. So when it ends, nobody will have failed. A machine will have finished, on a schedule set the day it was built. So here is the honest bottom line. The title of tonight's video is true, and it is true in a specific way that is easy to miss. Voyager will never leave the solar system, because the thing we call Voyager is not the aluminum. It is the machine that talks. That machine has about 4 years left, and the departure takes 30,000. What crosses the boundary in the year 32,000, and something is not a spacecraft. It is what a spacecraft leaves behind. There is a version of that which sounds bleak, and I do not think it is. The mission was funded for 4 years and 2 planets. It has now run for 49, visited 4, crossed a boundary nobody had measured, and is still returning data on a fraction of the power a toaster uses, maintained by a small team spending single watts to buy single years. Everything since 1989 has been extra, all of it. There is one practical thing you can do with this, and it is the reason I would not leave it as an abstraction. Voyager is still talking tonight. You can look up where it is right now, to the mile, on NASA's own tracker, and watch the number climb. You can listen to the golden record, which is free and online, and hear the 55 greetings and the whale song and the back. And on November 13th, you can note the date it becomes a light day away, which will happen whether or not anybody marks it. None of that changes anything, but there is a fairly narrow window, measured in a few years, during which this object is both extraordinary and still answering, and that window is closing. What is worth holding is the distinction between the machine and the object. The machine is nearly done. Somebody alive right now will read a log and find the last line. That will be an ending, and it will be a real one. The object is not done. It has barely started, and it will still be moving, on the same heading, at the same speed, long after every question anybody had about it has stopped being asked. Thank you for joining me tonight, on this trip out past the edge of the sun's reach. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. In November, it will be 1 day of light away. It has 49 years behind it and 30,000 ahead, and it will spend nearly all of them silent. Good night.